So here we're going to talk about the difference between polar bonds and polar molecules. And again, I am going to strongly encourage you to watch that Vesper video. That is the video on our geometry that is linked on our website. So here again, we're going to talk about polar bonds versus polar molecules. So when we have a molecular compound, we have two or more elements that are essentially fighting over these electrons. There's some kind of a tug of war going on, and one of the atoms is usually stronger and can pull the electrons towards itself. And when that happens, we say that it is a polar bond. So here's an example of a polar bond. So we see that chlorine can pull electrons towards itself. That's why we have this arrow pointed towards the chlorine. And we cross the back side of it, showing that hydrogen is now partially positive. It's lost some of its electrons. And we've also looked at this in the sense of chlorine being partially negative and hydrogen being partially positive. So any questions on the notation that I've just drawn on here, or anything so far about the idea of polarity? So when I think of polarity, I think of batteries. So batteries have a positive end and a negative end. So if we have a chemical bond or a molecule that has a positive end and a negative end, and again, here we're talking about partial positives and partial negatives, that's when we're going to be able to call it polar. So we'll be using these electronegativity values that we've seen before. Next up, we want to talk about the difference between a polar molecule and a polar bond. So I'm going to make a little table here. So polar bond, question mark, and polar molecule. Question mark. So we're going to decide if these have polar bonds and if they are a polar molecule. Oops. All right, so first off, we think about HCl. HCl is the molecule drawn right up here. So if we have a difference in electronegativity, I got accidentally muted myself for a second there. Did you guys hear what I was saying when I was drawing everything? Oh, no, okay, so you're just hearing me for the first time now? Oh my gosh, I'm so sorry. New computer stuff, I have a new trackpad that I've been using. Okay, so let's go ahead and start over again. I apologize. All right, so polar bonds and polar molecules. Oh, you could hear me when I was doing this right up here. Okay, good, good. I think I just muted myself accidentally. Did you hear me when I was drawing or writing the polar bond and polar molecules? Okay. So I think I just muted myself for a second, and I will move that trackpad out of the way. All right. So polar bonds. So here, what we're looking to see is if we have two elements that are different enough in electronegativity that they are polar. So here we have chlorine, which is a 3.0, and hydrogen, that is a 2.1. So if we do 3.0 minus our 2.1, we get a 0.9, and that's our electronegativity difference. Then we can look right over here, and it is indeed a polar bond. So what I'm going to tell you about most of our bonds is that for most bonds, if they do not have the same atom on both sides, we would consider them polar. Some notable exceptions will be carbon-hydrogen, because carbon and hydrogen are very close in electronegativity, and we see that a lot with our organic molecules. But most of the time, if you see, again, two different elements, they have two different electronegativities, and we end up getting a polar bond. So what we're going to see is if you can find even one polar bond inside of a molecule, you're going to say that there are polar bonds in this molecule. So here there are definitely polar bonds. Okay, any questions about why I could say that HCl has a polar bond? All right, so next up we need to know if this is a polar molecule. And what we're thinking is the molecule as a whole, do the electrons flow from one side to the other? And in this case, they absolutely do. They're going towards the chlorine. So they're moving towards the chlorine and away from that hydrogen. They are definitely flowing towards the right-hand side in this image. So whenever we have an overall flow of electrons, then here we are going to say that it is a polar molecule. So here HCl has a polar bond and it is a polar molecule. So any questions so far? All right, next up we're going to look at CO2. And here's our CO2, carbon dioxide. And the very first thing I want to do is forget about the molecule. And I'm just going to look at one bond. And I'm going to try to decide if this is indeed a polar bond. Remember, you only need one polar bond to make a molecule polar. So if this one was not polar, then we can go on and check the other bonds. But right here we have carbon and oxygen. So here's carbon at a 2.5 and here's oxygen at a 3.5. So if we were to calculate their electronegativity difference, and I always start with the largest number first, 3.5 minus 2.5, we have a difference of 1. And back to our table, that again falls into the polar or polar covalent category. So I can definitely say that there is a polar bond inside of CO2. So any questions on how we can say that inside of CO2 there is a polar bond? Which way will our electrons flow? Are they going to go towards the oxygen or towards the carbon? Excellent. I'm seeing a lot of oxygens, and that is correct because oxygen has the greater electronegativity. That's where the electrons are going to go. So they're always going towards essentially the stronger atom. And in this case, that atom is going to be the oxygen. So any questions about what we've talked about so far? All right, so next up we have another carbon and oxygen, and this oxygen again has a 3.5 for its electronegativity. So it is also trying to pull electrons towards itself and away from the carbon. So when you're first looking for whether or not you have polar bonds, you want to check all of your bonds in case if the first one doesn't work. So for instance, if our very first attempt didn't work and we said, hey, that's a non-polar bond, then I would check the one on the left. But we didn't have to do that in this case because we found that it was polar. Any questions about that idea that if you find the bond to be non-polar, you're going to go around and check all the other chemical bonds? Okay. So we definitely have a polar bond. Now we need to know whether or not we have a polar molecule. And what I want to do is show you that here we have one oxygen pulling to the right and one oxygen pulling to the left. Those of you who've had some physics or you've had some calculus and you've done some vector addition, you know that if you add an arrow going to the right plus an arrow going to the left, they cancel each other out as long as they're of equal strength, which they are in this case. So we say here that we have an overall dipole moment of 0. And once upon a time I told you about dipole moments, and I said that is a measure of how polar it is overall. And if it has a dipole moment of 0, it means it is nonpolar. So here, this is nonpolar overall, and the reason is because the polarity of the two oxygens are canceling each other out. One is trying to pull electrons to the right, the other one's trying to pull to the left. And in the end, nobody can win. They're equally strong, and nobody will ever win this tug of war. Uh-oh, frozen iPad. Sorry, frozen iPad. Give me just a sec. There we go. So I want to give you some rules for how we're going to determine if a molecule is nonpolar. And they must fit both of these rules. So if they only fit one of these rules, it doesn't work. So this is for our nonpolar molecules. They need to have a symmetrical shape. And the outer atoms must be either the same or very similar. And by very similar, I mean having similar electronegativities. All right. Any questions on anything here so far? So let me give you a minute to copy all this down. All right, how are we doing? Anybody want this page for a little bit longer to copy? All right. So let's go back here. First of all, would you say that this has a symmetrical shape? Yes. All right, so what I'm going to be doing with you in a little bit is going over all of the symmetrical shapes, but I see lots of you responding with a yes, excellent, so this is definitely a symmetrical shape. Then what I mean by the outer atoms are these ones right over here. Sorry, it's not the best color for highlight. Let me try again. This one and this one. So these are the outer atoms. The central atom would be carbon, the outer ones are oxygen. So if they are the same or they have similar electronegativities, then we are going to say that this is a nonpolar molecule overall. So it is possible to have a polar bond like we do in CO2, but have a nonpolar molecule so long as it is symmetrical and all the outer atoms are the same or very similar. So any questions on anything here? Okay, so before we go on, I want to talk to you about the symmetrical shapes. So we don't have that many symmetrical shapes, so I think it's easier just to remember which ones they are. Those of you who had Chem 2 or Intro to Chem class, you probably remember these from your good old Intro to Chem days. These are your VSEPR shapes. Those of you who it's been a while since Chem, your Intro to Chem class, make sure you watch the video. So here, our symmetrical shapes are going to be linear, which is the one we just looked at with CO2, trigonal planar, and tetrahedral. Notice these three are all shapes that don't have any lone pairs, any extra electrons on the central atom. So here, I'm going to say symmetrical shapes. So any questions on anything here so far about linear, trigonal planar, and tetrahedral being symmetrical shapes? Okay, so the other shapes, I'm going to go ahead and modify them just a little bit. Where it says E, those are actually electrons. So I'm going to take off the E, and I'm going to replace them with actual electrons so we can see how they are not symmetrical. There we go. All right, so bent and trigonal pyramidal or trigonal pyramid, those are not symmetrical shapes. So only the ones here that I have highlighted in yellow or orangish, those are the ones that are symmetrical on this page. So any questions about why those ones I highlighted are symmetrical and why the other ones are not symmetrical? Okay. So let's move on to some new structures. So for most of you, these structures are going to be new. That's okay. You'll learn about them in the Vesper videos. So here we have trigonal bipyramid or trigonal bipyramidal, and we have octahedral. We also have square pyramidal and square planar. Then we have seesaw, T-shaped, and linear. And again, I'm highlighting our symmetrical shapes. I'm going to go ahead and modify these ones with electrons so you can actually see the electrons. So you can see how they are not symmetrical. Except I should say the square planar and the linear. All right, so the ones that I have highlighted are symmetrical shapes. The ones that I did not highlight are not symmetrical shapes. So with respect to our polarity of our molecule, we need a symmetrical shape. So it is either going to be linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, square planar, or linear. Those are the only shapes that are going to be those ones are the only ones that are going to be symmetrical, and it's my recommendation that you just memorize those so you will know right off the bat if you're looking at a symmetrical shape. And I see a question coming through. Let me move a window so I can see it better. So good question. So I have a question saying symmetrical means they have all bonded pairs, and I'm going to interpret that as saying no lone pairs. So last semester in Intro to Chem, you probably saw something like so, and you might have learned the rule that if there is a lone pair, it's not symmetrical. But that doesn't apply this semester when we look at these shapes right here. We call these expanded octet shapes, and that is because all of the central atoms have more than 8 electrons. So it is possible to have lone pairs on the central atom. And does X stand for a single element, or can it be different? So X stands for any single atom, although I suppose you could say next semester when you get into 1B, you're going to learn that sometimes that could be like NH3 there. So next semester you'll learn about attaching more than one element, but for our class we'll focus on just one element being attached. All right, so other questions or follow-up questions to the ones that were asked in the chat box? Okay, so our rules here are that we must have a symmetrical shape, so it's got to be one of the ones that are highlighted, and then the outer atoms must be either the same or have similar electronegativities. All right, so here is our water molecule. So first off, and I know most of you haven't had a chance to watch the videos yet, but does anybody know what shape this is? Excellent, this is bent. And I know I just showed it to you a moment ago, but is bent symmetrical? Excellent. It is not symmetrical. As soon as we know that this shape is bent and it is not symmetrical, I can immediately say it is a polar molecule. So the shape alone can tell us whether this is a polar molecule. If it is not symmetrical, it is immediately a polar molecule. Doesn't matter if the outer atoms are the same. In this case, you do have the outer atoms the same. Doesn't matter. Still polar because of that shape. So any questions on why I can say right away that this is a polar molecule based on the fact that it is not symmetrical? All right, so next up, we've got to decide whether or not it has polar bonds. So I'm going to look at just one of the bonds. Let's get rid of the other one. All right, so I'm looking at just the hydrogen and oxygen. Oh, good question about how do we determine it was bent. Give me just a moment. So let's look at this chemical bond between oxygen and hydrogen. So oxygen is a 3.5, hydrogen is a 2.1. And let's see. If I am correct, that is what, 14, 1.4. All right, so this is definitely a polar molecule with a 3.5 and a 2.1 here. So here we see the electrons are going to flow towards the oxygen and away from the hydrogen. So this definitely has a polar bond. Any questions on how we determine that this has a polar bond and it is a polar molecule? All right, so just looking at our molecule overall, we have electrons flowing towards the oxygen on both sides and away from the hydrogens. And so what we see is a net flow of electrons going upwards. Let me move this a little bit. We have a net flow going upwards. So we have an arrow going up and to the right and an arrow going up and to the left. Therefore, it's overall going to be polar moving up. And I see a couple questions coming in. So questions about first why it's a polar molecule and two, how we determine that it's bent. So we knew it was a polar molecule as soon as we saw that it was bent. So let's go back and take a look here. So the only symmetrical shapes we have are the ones highlighted. So we actually have two types of bent, and this is the bent we're actually looking at right now. So anytime you have a bent molecule, it is polar just by its shape. So I'm going to talk about, in just a sec, I'll talk about how we know it was bent. But any questions on once we know it's bent, how we know that it's polar? Excellent. All right, so the next thing is how we know that it is bent. And the video is going to go into a lot of detail on this, but let's just talk about it briefly now. If you were to do the Lewis structure of water, it would look something like so. And what we see is a total of 4 electron groups or electron clouds. So I see 1, 2, 3, and 4. So a total of 4 electron groups or electron clouds and 2 lone pairs. And our lone pairs are going to be this and this right here. So then we can go to our chart. And here are electron groups. It's also called a steric number. So total of 4 with 2 lone pairs. And that's our bent right there. So any other questions so far? Excellent. All All right, for those of you who are doubting, water definitely is polar, and we can see it in this electron distribution map. So this is one of those computational analysis graphics that we come up with, and that app that I was showing you, they updated it and they moved stuff around, but I found all the correct buttons, and I can show you that again sometime. So you can actually make one of these yourself, which is super cool, and it's a free app. So just imagine you have little kids at home that want to paint. You don't want them to get all messy. You're like, hey, you wanted to paint? I'm going to give you some electrons to model. I'm going to give you some molecules to model, and it'll be just as pretty as your painting. All right, but here you can see up at the top, this has more electron density. That's why it's in the red. And down here where the hydrogens are, you can see it in the blue. That's showing that it's partially positive. So blue shows a positive charge down there, or a positive partial charge, I should say. All right, so questions on anything here for a water molecule? All right, any questions about the rule that we just came up with? Or I should say the two rules for nonpolar molecules. They both must be symmetrical, and their outer atoms must have be the same or have very similar electron negativities. All right, so yes, there's a polar bond, and yes, it is a polar molecule. So we're going to do a bunch more examples, but questions on anything? All right, so polar bonds versus polar molecules, and I'm going to start off with that O3. If you didn't know, this O3 is ozone. It is the same ozone that is up in the ozone layer. Also, if you didn't know, ozone is actually hazardous to your lungs, so we don't want it down on Earth. On Earth, it is considered a pollutant, but up in the upper atmosphere, up in the ozone, it is very essential. All right, so number one is ozone, and ozone looks something like so. And again, I know you guys didn't get a chance to watch those videos yet, but if you had to guess, anybody know what shape this would be? Anyone want to take a guess on that shape? All right, so I'm seeing bent. Yes, this is definitely bent. Just for the fun of it, let's go ahead and talk about why it's bent. So there's actually two types of bent. And here I'm going to say 1, 2, 3 electron groups. And one of those electron groups, this one right up here, is a lone pair. So let's go back to our chart. And yes, Jervin, you are right. There is a resonance structure for this. So let's go ahead and check out why it's bent. All right, so electron groups, it has 3, had 1 lone pair, and therefore it is bent right here. So 2 different types of bent. This one is this one right up here. And Jervin recognized that this absolutely has a resonance structure, so let me move this on over. So if you were drawing this on a test or quiz, you would also draw its resonance like so. Because there were 2 locations that double bond could have been in. It could have been on the left, or it could have been on the right. So yes, it definitely has a resonance structure. All right, and so the electron groups are officially the chemical bonds right over here, and the lone pairs. So officially it's those electrons that are directly in contact with the central atom. And yes, we only count the lone pairs on the central atom when we're looking at the shapes. Yeah, good questions. All right, so now that we know that it is bent, we're trying to figure out if this has polar bonds and if it is a polar molecule. But let's start with the polar molecule. Do you think this is a polar molecule based on its shape? Excellent. It is absolutely a polar molecule based on the shape alone. Remember, in order for it to be nonpolar, it has to have a symmetrical shape and the outer atoms have to be the same. Here we do not have a symmetrical shape, so it is a polar molecule because it is bent. And this is a really weird one. This kind of messes with your head a little bit because you're like, how can it be polar? They're all oxygens. So if I was to only look at one of the chemical bonds, so for a moment, I'm going to pretend the other chemical bond isn't there. This is an oxygen-oxygen chemical bond. So by definition, they must have the same electronegativities. So that is not a polar bond. Oops. Likewise, I could white out the other side and look at only the bond on the right. And again, it's a nonpolar bond because they're both oxygen. So again, they're fighting, but they're equally strong. They have the same electronegativity because they're the same element. So what makes this one really unusual is that we have a non-polar bond, but we have a polar molecule. The way that works out is you have these oxygen pulling down, and you have one oxygen pulling up. So you imagine that there are triplets, and two of the oxygens are pulling down. Two of the triplet pair want to go one direction, and one wants to go the other direction. Overall, you're going to have an electron flow going downwards because you have two pulling down and only one pulling up. So again, this is one of the very strange ones. We don't see this very often. But any questions on why there are no polar bonds here, but it is a polar molecule, and you can think of the polar molecule as based on that shape alone? So we do have experimental evidence for this. This is one of the computational models, but we do have true experimental evidence where we put our molecules into a machine and we tested the polarity of different parts of it. But here it's not a huge difference. It's very slight. But you can see right along the edges here, there's just a little bit of red showing that partial negative. And then up here, there is a very small amount of partial positive. So it's a very small difference in difference in polarity, but it is there. All right, so questions on anything here? All right, so next up, we're going to take a look at these molecules right here. And we'll start off with our HCl. So this one we've already taken a look at. We know that chlorine is going to pull the electrons to the right. So partial negative here and partial positive over here. And I realize we actually didn't finish the previous slide, so let me go back to that. But any questions about that HCl that we're looking at? Okay, sorry about that. We neglected to go on to our next slide, or finish our previous slide, I should say. All right, so next up was the HCl, and this is the one that we started this section with. So here we said that chlorine is more electronegative, so electrons are going to flow towards that chlorine. So we said that it did have a polar bond. Next up for polar molecule. Let's think about our rules. So first rule was it needed to have a symmetrical shape. So this is linear. So let's go back to our table. So here is linear. What you're seeing is a slightly different linear here, but it is still linear, and linear is one of our symmetrical shapes. So we've met the first rule. This is a symmetrical shape, but the second rule says the outer atoms have to be the same or very similar. So here the chlorine and the hydrogen are very different elements. They have different electronegativities. And therefore, even though it has a symmetrical shape, it is still a polar molecule. If we had had two hydrogens or two chlorines, then it would be nonpolar because it's both symmetrical and has identical outer atoms. But here it is a polar molecule because you have different elements on the outside here. So any questions on why this is a polar molecule and it has a polar bond? Okay. Sorry, I keep scrolling back and forth. All right, so next up is our BF3. All right, so if we were to draw this out, we're going to start with the boron in the center, and we have fluorine all around. And it's going to look something like so, and I know I'm going really fast for a Lewis structure here. That is only because I have done this many, many, many times. All right, so here we have BF3, and we're looking to see if it has polar bonds and if it's a polar molecule. So let's start with the polar molecule. Anybody recognize that shape? I know we just started looking at those shapes. Okay, so let's go ahead and find it on the chart. Oh, it is trigonal planar, yes. So it is triangular, but it's a trigonal planar. So let's go ahead and look at it on our chart. So 1, 2, 3 electron groups and no lone pairs. All right, 3 electron groups, no lone pairs, and here it is. It is trigonal planar, and it does look very triangular. So it is one of our symmetrical shapes. So it has passed that test. All right, so the first test was that it had to be symmetrical, and it is symmetrical. What was the second test? What was the second rule it had to meet? It has to be symmetrical, and what else? Outer atoms, the same, yes. Excellent. And I see a question coming in about lone pairs. Give me just a moment. So yes, so outer atoms are going to be similar or same electronegativity. So based on everything we've talked about, do you think this is a polar molecule or no? So I'm seeing yes and no. What do you guys think? Let's go back to our rules and take a look there. All right. Did it have a symmetrical shape? Yes. Were the outer atoms the same or similar? Yes. Therefore, we are nonpolar. Any questions on this that we met both rules, and the guiding principle, let's call it, was that we needed to meet both. So we met number 1 and number 2, therefore we are nonpolar. So any questions on why we would call this a nonpolar molecule? All right. All right. Any questions on that one? Okay, and I saw a question come in about lone pairs. Let me get back to it. Let's see, it says, would it always be known when there are lone pairs? Do you mean would the symmetry always be known or the polarity always be known if there's lone pairs? The symmetry. Okay, good question. So back when you were in Chem 2, before you looked at these structures, these are our expanded octet where some elements have more than 8 electrons. You can use that rule that says if they have lone pairs, they're not symmetrical. But now in Chem 1A, you have 2 that violate that rule. So these 2 right here do have lone pairs, but they also are symmetrical. So one thing you could remember, if it's easier for you, is to say there's no lone pairs on the central atom. It's immediately symmetrical, and then just remember the 2 extra shapes you have, which is linear and square planar. So that's another way to remember it without having to remember all of these individually. Just thinking no lone pairs, it's symmetrical, and now you've got 2 extras to memorize. All right, so other questions so far? All right, so next up is the polar bond. And we're looking at boron and fluoride. Here is our boron, and here is our fluoride. So we have 4 for fluoride and 2 for boron. All right, so what do you all think? Is this a polar bond? So I'm seeing no's and yeses. So it looks like yeses are becoming more popular. So this is considered a polar bond. It's actually on the verge of becoming ionic. It's so polar. So 4.0 minus 2.0 gives us a 2.0. So I would go ahead and characterize this as a polar bond. If you wanted instead to characterize it as ionic, you could. So you could call this polar or ionic. Essentially, there's a really large difference in electronegativity. So yes, you could characterize it as ionic as well. But it is definitely not a nonpolar bond. So yes, I do see that the chart characterizes 2.0 as ionic, and I promised you guys that I wasn't going to give you any molecules that fell right on that line, so I apologize for that. 2.1 would definitely be ionic, yes, absolutely. Okay, so how are we feeling about these so far? Easy peasy. All right, good, good. People rarely say that about the polarity. This is one of the ones that people hate. All right, so I'm going to have you try the next few. I'm going to draw them out for you, and I'm going to have you copy them down, and then I will flip so that you can see the electronegativity page. And what you're seeing right here is you're seeing what we call a wedge or a caret. That's showing that you've got a hydrogen coming out at you, and a dashed line means it's going away from you. So this is showing our tetrahedral. All right, so go ahead and copy down these ones, and then I will move to that electronegativity chart.
Sir, for number 5, you did H's instead of CL.
Oh, I did. I'm so sorry. Thank you. I'm so used to doing CH3. And the other ones, oops, the other ones I all did correctly. Good question. So I see a question coming in. So when you're subtracting electronegativity, which element is subtracted from which? Really, you can do it in either order. I always like to do the large number first. That way I always get a positive difference. But if you did it the other way, just take the absolute value of your answer. So just make sure the difference is always positive, and then it doesn't matter. So the wedges are showing you geometry. So a wedge means it's coming out at you, and a dash means it's going back behind you. So here a question about the 1B this summer. So we are considering opening up a second section. So if you are interested in it, I would jump on that wait list. And my hope is that either we will expand it to a double section, or we're going to get a second section going. And I'm hoping that we'll give all the waitlisted students priority. I am waiting to hear back from the department chair. Last time I talked to him, he was going to check into it and see if he could add or turn it into a double section. So we're just waiting for the final verdict, which I think he was talking to the administration. So for the online waitlist, you just go ahead and register for the class, and it'll place you on the waitlist. And I know it's a long waitlist right now, but if we can get that, yeah, so that's the thing, that if we can't get a second section, then my hope is that we can just let everybody into the online class. So that's why it's best to just get on that wait list. Yeah, when they first set it up, the limit was by how many students could fit in the lab, but now we don't have that limit. So yeah. All right, so where we left off was with number 4, which is our NH3. All right, so here we're looking to see if we have polar bonds. Go ahead and say polar bond. And if it is a polar molecule. All right, so let's start off with the polar bonds. So is there any polar bonds in number 4? Excellent. So there is definitely a polar bond in there, and in fact, there's 3 of them. Any questions on how we could say that there's a polar bond inside of NH3? All right, so what about the molecule? Is the molecule polar? Yes, absolutely. It has a non-symmetrical shape, so it is immediately polar. So any questions about NH3? All right, so next up we had carbon tetrachloride, CCl4. Did it have any polar bonds in there? Yes, definitely. Any questions about why we could say it has polar bonds? All right. All right, so is it a polar molecule? Correct. This is not a polar molecule because this is a symmetrical shape. This is tetrahedral, and we see our outer atoms are all the same. So any questions about that idea that it has polar bonds, but it is not a polar molecule? All right, so here we have CH3Cl. Does this have any polar bonds in it? Yes, it does, and it is one polar bond. You're right, just the carbon chlorine. Is it a polar molecule? All right, it is indeed a polar molecule. So it does have a symmetrical shape, but there's one problem. The outer atoms do not match. That chlorine is not the same as the hydrogens. So any questions on this number 6 or any of the other ones?
If it were, let's say, for example, if it were a carbon with 4 hydrogens surrounding it. Would the answer polar bond be no? They'd all be covalent?
Correct. These would all be pure covalent bonds. So for this one, if this was one of ours, there would be no polar bonds and it would be a non-polar molecule. You're right. All right, so I see a question. You're welcome. So I see a question about NH3. So NH3 does have the outer atoms the same. However, the shape is the problem. So let's take a look at our shapes. Actually, before we take a look at our shapes, let's look at our electron groups. So we've got 1, 2, 3, 4 electron groups. And one of those electron groups is a lone pair. So here are 4 electron groups with 1 lone pair, and that makes it trigonal pyramidal. So the fact that it is not symmetrical immediately makes it polar. And then I see a question from Tasso as well, but Maria, did that sort of make sense why it's polar? Yes, so Tasso, it is trigonal pyramidal. Yes, okay, perfect. All right, good questions. Any other questions so far? All right, so here's the one that I tried to prematurely get into. So here are all the shapes that we just looked at, but here they're all drawn out. So here is our carbon tetrachloride. So we have carbon in the center, 4 chlorines around the outside, and it is nonpolar because the shape is symmetrical and all the outer atoms match. Here's our ammonia, NH3, and this one is polar. So it is trigonal pyramidal. So its shape alone makes it a polar molecule. Here we have our CH3Cl, and even though it has a symmetrical shape, the fact that we have only 1 chlorine and the other 3 are hydrogens makes it polar. So the outer atoms don't match. And here's our BF3. So this is a symmetrical shape and all the outer atoms match, so this is nonpolar. So any questions on anything here so far? All right, so let's do a few more together. So our first one is going to be BrCl. And here we're going to do the full Lewis structure. So here, each of them have 7 valence electrons for a total of 14. Oops. There we go. BrCl. And I just used 2 electrons, so now I'm going to say 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So now these are bonded together. So our questions again is this a polar bond? And do we have a polar molecule? So here is our Br and our Cl. They're extremely close. They have an electronegativity difference of only 0.2. So in terms of a polar bond, I'm going to say it is not a polar bond. They're very close in electronegativity. Any questions about why I'd say the BrCl bond is nonpolar? Let's see, do we need a double bond? 2, 4, 6, 8, 10, 12, 14. And around bromine, we have 2, 4, 6, 8. And around chlorine, we have 2, 4, 6, 8. So it doesn't look like we need a double bond. Oh, no worries, no worries. It's always good to double check. All right, so any questions about why we would say that this is not a polar bond with an electronegativity difference of only 0.2? All right, so I'm going to say that this is a nonpolar molecule. So the atoms aren't the same, but they are extremely similar. So similar that, again, they only have a 0.2 difference in electronegativity. So they are linear, which is a symmetrical shape, and very close in electronegativity. So any questions on number 6 here?
Difference of negativity when you start considering the molecule to be polar, like 0.5 or like 0.4 difference.
Yeah, so I would say around 0.4, 0.5, right around here is where we start considering it to be polar, like so, yeah.
Okay.
Yeah. All right, so other questions so far? All right, so then let's do our SO2. All right, so we have sulfur and we have 2 oxygens. So it looks like 6 times 3 would give us 18. So I have sulfur surrounded by the oxygens. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. All right. Is sulfur satisfied? Does sulfur have enough electrons? Excellent. So what should we do for sulfur? All right, so I'm hearing a double bond. So I'm going to take 2 electrons off and bring it in for a double bond. But for those of you who are saying why on the left, why not on the right, we actually do them both, and that was our resonance. Like so. Okay, any questions on how I did that Lewis structure? All right, so let me draw this out the way it would look. It is a bent molecule. And I'm just drawing one of the resonance structures here. All right, so sulfur and oxygen. We have oxygen at a 3.5 and sulfur at a 2.5. So what do you think? Is this a polar bond? Yes. And I see a question about whether or not you need to know the shapes, and you do need to know those shapes. So I'm hoping that the ones on the first page, those are ones from Intro to Chem, and I'm hoping most of you already remember those from Intro to Chem, and it's only the second page that is new. But if not, I do need you to learn them all. Yeah, sorry. All right, so next up is the polar molecule. What do you think? Is this a polar molecule? All right, excellent. So I'm seeing yes. And this is a polar molecule, even if all we look at is the bent shape. See, can we have another double bond on the other side and 2 lone pairs? Interesting. So in the video, you're going to actually learn about how... Oh, actually, I think you probably saw that from the video, right? You saw the formal charges. Is that what you're talking about, Clinton? Yes. Okay, so that's what you're thinking of. So let's actually take a look at those formal charges to see the best structure. So Clinton brings up a really good point. Oops. All right, so let's take a look at these formal charges. So if I'm looking at the oxygen, oxygen initially has 6 valence electrons, and then I count its connections. 1, 2, 3, 4, 5, 6. So it has a formal charge of 0. This oxygen over here, though, initially started with 6, and I count its connections. 1, 2, 3, 4, 5, 6, 7. That's a -1. And right over here, we have sulfur that started with 6. And I'll count its connections. 1, 2, 3, 4, 5. And that is a +1. So there is a better way to write that Lewis structure once you do your formal charges, you're right. That would look something like so. And from here, this would have a 0 formal charge, this would have a 0, and this would be 6 minus 1, 2, 3, 4, 5, 6. So now everything would have 0 formal charges, so you're right, this is a better structure for it, but in terms of what we're doing right now, it will still look similar, it will still be bent, so this would still be a polar molecule, but you're right, there is a better structure for this one. All right, other questions about our SO2? Anytime. Oops, my iPad is jammed. All right, so questions on anything with that SO2?
Since S is in the third period, it can hold more than 8 valence electrons, right? Or no, 3 can hold something along those lines. I can't really remember.
So you were right, Jervin. So it can have more than 8 electrons because it's in the third period and below. Yes, or it's in the third period, but any element third period and below can have more than 8 valence electrons. You're right. And I see from
Cool.
And I see from Andrew, how do we know when to decide if we need to consider the formal charges? So on a test or quiz, I will tell you draw the best Lewis structure, and it'll have best in capital and probably bolded and underlined. That's when I want you to check your formal charges. But truthfully, it's never a bad thing to do it all the time. All right, other questions on this one? All right, and finally, our SF6. And this is right. All right, so here we have a sulfur, and it will be surrounded by 6 fluorine. All right, so it looks something like so. And we want to know if it has polar bonds and if it's a polar molecule. So let's take a look. First at our fluorine and our sulfur. So what do you guys think? Do we have a polar bond in there? All right. I think I got a couple of brave souls, a few of you saying yes. Any questions on why we would consider this a polar bond when we have 4 minus 2.5? All right, so next up we need to consider the shape, and this is one of the new shapes, and let me straighten out this F a little bit right here. This is one of the new shapes that you probably didn't see last semester. This is the octahedral right here. The octahedral has 6 atoms connected to a central atom, so it is definitely an expanded octet. Central atom has more than 8 electrons. All right, so it is a symmetrical shape. All the outer atoms are fluorine. So is this a polar molecule? So I'm seeing yeses and nos. All right, but I'm seeing a lot more nos. All right, so the answer is no. It's a symmetrical molecule and all the outer atoms are the same. So any questions here on number 8 about why this would be a nonpolar molecule that has polar bonds? So a lot of people consider this to be one of the tougher concepts, both in the intro class and in this class. So feel free to let me know if you have any questions on this. All right, so we're going to go forward just a little bit longer, and then we'll start talking about the lab. So here we have our covalent bonding and orbital overlap. So here we're trying to visualize how exactly these covalent bonds get made. So right up here we have 2 hydrogen, and they approach each other, and then they actually overlap each other. And I like to think of them as actually kind of holding hands. It's a very firm grip that they have on each other. But it is this overlap that we call a covalent bond. And that's what kind of why I like to think of it as holding hands, because you're definitely overlapping hands as you have that nice firm grip. So any questions on this so far, that idea of that covalent bond being an overlap in the orbitals, like a nice firm grip? All right, so here the idea is the hydrogen atoms are going to move together because the nucleus on one, which is positively charged, is attracted to the electrons on the other, which is negatively charged. So that's why they have an attraction, because of the positive in one of their nucleus and the negative on the electrons from the other. So here we have again the positive and the negative that are attracted together. There is another problem, that is that the electrons are repelled from each other and the nuclei repel each other. So it's kind of a push and pull, and the idea is they kind of float together, maybe they get a little too close, and then they find their perfect spot. And that perfect spot is where they balance the attraction and the repulsion. So it is a favorable interaction. It happens spontaneously, it happens all on its own, and it lowers the potential of the atoms. So in chemistry, we're always moving towards lower potential energy. We're always trying to go from high to low, trying to get to more stable. So this would not happen if it didn't create a more stable molecule. Here's a graph, and it's showing you kind of from right to left, which is, I know, a little weird, but showing you the atoms kind of flying into each other. So I'm going to start here on the right. So here are atoms, and I know they look like googly eyes there. So they're flying in towards each other, and the red line here is showing the energy. So here they are flying in towards each other. As they start to overlap, notice the energy is going down significantly. That is what we want. We want a lowering of the energy. And they get even closer. And here they are. Now they have that nice overlap that we expect from the covalent bond. Now it is possible for them to get too close. So you may have a significant other or a best friend or even a pet that sometimes they just get too close. I often wake up and there is a cat on top of my face that's a little too close for comfort. And when these atoms get too close, the energy shoots up, and that is a bad thing. So they have to find that perfect spot where they are overlapping, but they are not so close that they have repulsion between the two nuclei or between the two electron groups. And when they find that perfect spot, that lowest energy spot, that's what we consider the bond distance. So we take the bond distance as the distance between the two nuclei when they are overlapped at their lowest energy. So any questions about that? Okay, so here it says if the atoms get too close to each other, the two nuclei, which are both positive, would repel each other, resulting in higher potential energy. So again, what we think of as bond length is the distance between the nuclei at that lowest potential energy. So it's right over here, the distance between the nuclei when they have that lowest potential energy. That is their most stable form. So any questions on anything here? All right. So next up, we're going to talk about the idea of this valence bond theory, and that's actually what we've been looking at. It has to do with the overlap of orbitals, and that's how we're visualizing these covalent bonds. So the overlap of the orbitals is what creates the electron density between the nuclei that we think of as the covalent bond. So we've already taken a look at hydrogen, and hydrogen looks sort of like so, and I'm drawing s orbitals, and they overlap, and this is our covalent bond. But it doesn't have to be two s orbitals. For instance, we could have our HCl, hydrogen, which is our s, and chlorine, which will overlap with a p. This could also be our covalent bond. So it could be an S and a P overlapping, or we could have two P's overlapping. This is also considered a covalent bond. So truthfully, anytime we have two orbitals that are directly overlapping, that is our covalent bond. It does not have to be two S's, but it can be. Here we see it with two S's. We see a S and a P, and we see two P's. All right, so any questions here about this direct overlap? All right, so next up we're going to talk about the idea of hybrid orbitals. So it says, what if orbitals weren't the way we normally think about them? What if we could mix the S, the P, and the D orbitals all together? I think of it as throwing in a blender and making a smoothie. So it says, what if we put the orbitals in a blender and made hybrid orbitals? So smoothies are hybrids. They're a mixture of all the fruit that you put in. And our hybrid orbitals are the same. They're a mixture of all the orbitals you put in. And just like a smoothie, if you put in more bananas, your smoothie is going to taste more like banana. What we find is if you have more p orbitals, it's going to look more like a p. If you have more s orbitals, it looks more like an s, and so on. So here is what I like to call the SP smoothie. So here we're going to mix one s and one p orbital. So the first rule is that if you put two orbitals in, you must get two orbitals out. And those two orbitals will be identical, but they are going to be going in different directions. So here we're doing an sp orbital, and the result is going to be 50% s, 50% p. So if you put a peach and an apple into the blender, imagining the fruit is about the same size, it's going to taste about 50% like apple, 50% like peach. Same thing here. It's about 50% S and 50% P. And if you want to go back later on, I've been having trouble with these links, but you can get that link to work. There was a really nice animation, but I've been having trouble with that link getting it to work. So this is what our hybrid orbital looks like. So our hybrid orbitals, they're always going to have one large lobe and one small lobe. And one way that I remember these is, to me, that kind of looks like a whale. That they sit together. So here is one. And here is the other. Now they have these little, what I like to think of as tails. They're actually the small part of the smaller lobe. And what you're going to see is that they're often omitted. So you often just see them looking something like so. Some images will show them as a little dotted line in here. But these remind me of when you tie two balloons together. Those little ties in the middle, you just don't really notice them because you have these giant balloons. And it's the same thing. We have so little electron density hanging out in this area that sadly we often just forget about it. And we often just think of them like so. And sorry, those should be the same size, but as you can tell, my artwork not perfectly symmetrical. There we go. Best as I can do there. Okay. So I want to show you how you get one small lobe and one large lobe, but any questions on anything so far? Sorry, I was going to draw it out, then I couldn't remember if I had created a PowerPoint for it. All right. So here I'm going to look at a p orbital, and I'm going to look at an s orbital. So once upon a time, a long, long time ago, I told you that these came from a solution to what we call the Schrodinger's equation. Sorry. And that equation has positives and negatives. They are not charges. These are all negatively charged. The orbitals are because there's electrons running around. However, there are charges in the equation. And in a p orbital, one is positive and one is negative. Sorry. Now for your s, it could be either positive or negative. So here, if we were to combine these two, when the two positives come together, we call it an additive attraction. So you get one large, and then you get one small when you have the positive and negative combined. Sorry about that. And that is very similar to what you would see in physics. So if you were in physics, and you had two waves that were in phase, and you added those together, you would increase your amplitude like so. However, if you had two waves, and here I'm going to make them perfectly out of phase, as perfectly as I can do. So they're perfectly out of phase, you will get a straight line. So it's the same way with our charges. If they have the same charge, it's going to be an additive combination. If they have different charges, then it's going to be a subtractive combination where they subtract from each other. It would only become a flat line if they were perfect opposites. If they're just slightly opposite, then it would just diminish the size. And that's why we get one large lobe and one small lobe. But that is just kind of background. And by background, I mean I'm not going to be testing you on it. So any questions on anything there? Or anything that we've talked about so far with this idea of the hybrid orbitals? Okay, so here are the sp hybrid orbitals, and on the right hand side it says the large lobes are only shown. What that means is those tiny little lobes aren't just cut out of the picture. It's very sad, but there they are. They're in there a little bit. So these are two different orbitals, two different sp orbitals that are put together. Okay. So the question is, well, why on earth do we need hybrid orbitals? We were just fine with our sps, ds, and f's. They can live their own life. They can do their own thing. Why do we need to put them together? And the answer is actually that VSEPR that y'all are going to watch the video on. So the shapes that you see in VSEPR, whether it is linear, trigonal planar, tetrahedral, or any of the others, we cannot make them with our orbitals. So we had this theory about all these orbitals being s, p, d, and f, but they don't fit the shape that we know of for these molecules. So we run these molecules through our machine, and it says, hey, this is tetrahedral, and somebody starts trying to play with these orbitals, saying, well, how do I make these orbitals tetrahedral? They have to do it somehow, because we know that we have a tetrahedral molecule, but there's no way we can fit them. And that's how these hybrid orbitals were sort of born. We had to find a way to make the orbitals match what we see from our molecules in the lab. So here it says we know that BH3 forms trigonal planar, but how to get those orbitals to line up into a trigonal planar molecule. So putting these together, there's no way to make trigonal planar. And again, that's why we had to come up with these hybrid orbitals. So the hybrid orbitals help us to explain our VSEPR shapes. So next we're going to look at BH3, and I call that sp2 smoothie. So here what's going on is we're taking one s and two p orbitals, hybridizing them, and now we have three separate orbitals. These three orbitals are going to get as far apart from each other in space as they can, and that is how they form the trigonal planar. So the idea of VSEPR is it's valence shell electron repulsion. So these electrons are pushing as far apart as they can be, but they are not the regular orbitals that we know of. They are these hybrid orbitals that are engaging in the shapes that we know of as Vesper. And I'm going to show you how to figure out that it is an SP or an SP2 in just, well, either today or next class. But any questions so far about what we're doing here? All right, so here are our hybrid orbitals, and I lied, I'm going to show you how to do it right now. All right, let's do the SO2, and let's go ahead and use Clinton's idea of doing the best possible shape, which is like so. So here's the best Lewis structure for SO2, even though they could also be drawn with a double bond on one side and then resonance. This is a better structure for them. All right, so I'm going all the way down here to show you the instructions. So first you draw the Lewis structure, and then you count your electron groups. Then you're going to find the hybrid orbitals that are needed to accommodate the pairs in the geometric arrangement, and you must use this order right here. So S, P, 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 D, 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 D. So where I got the numbers is that there are 3 p orbitals and there are 5 d orbitals. So there's only one s, so 1 s, 3 p's, and 5 d's. So let's go over how we're going to do this. So every time I recommend you write out your 1s, your 3 p's, and your 5 d's, like so. Now you look around your central atom and you see how many electron groups there are. So a double bond counts as a group. So we got 1, 2, and 3. That lone pair also counts as a group. So we need an orbital for each one of those. And so I'm going to say 1, 2, and 3. And this is what I need to hybridize. So I will call this sp2 like so. So any questions on how I came up with this being an sp2? All right, so let's take a look at the next one. So here is carbon. So carbon surrounded by 4 hydrogens, 1, 2, 3, 4 electron groups. Now I'm going to write this out. S, 3 p's, and 5 d's. So there are 4 electron groups. And yes, I see the question. Good question. We only count electron groups on the central atom, so we ignore them on the outer atoms. Good question. At least for right now we are, because we're only concerned about the hybridization of the central atom. Later on we'll talk about the hybridization of the outer atoms. So here, 4 electron groups, and so 1, 2, 3, and 4. So I'm going to call this an sp3. All right, so any questions on this one here? Okay, so I think for lecture, I'm going to go ahead and leave it here. So for our lab, we're probably going to talk for about 15 or 20 minutes. Do you guys want to take a 5-minute break or a 10-minute break? All right, so lots of 5s coming in. Let's go ahead and take that 5-minute break, and let's come back at 8:05. And then we'll talk about our lab. And it is lab number 12 that we're working on today.